My dear students, in this class we are going to look at asynchronous counters. Asynchronous counters are also known as, in short, ripple counters. Okay. These ripple counters we are going to design now. It is very simple and easy way. The way we have designed the number of flip-flops required for any counter is same based on the count value. Let us suppose if at all I want to build a 4-bit ripple counter or asynchronous counter, I need 4 flip-flops. For example, if I design mod 12 counter, asynchronous counter, still I need 4. Why? Because 2 power n should be greater than or equal to capital N. 2 power n should be greater than or equal to 12. So when n is equals to 4, 2 power 4 is 16, is greater than or equal to 12. So in this way, we can find the number of flip-flops. Once flip-flop is, if you find how many required, then which flip-flop we need to look at. Let's suppose if it is T flip-flop, directly no issue. If it is JK flip-flop, we convert it into T. How to convert JK to T flip-flop? Very simple. You take JK, you make J is equal to 1, K equal to 1, you give the clock, then it is going to act as a T flip-flop, Q bar. Okay. Let's suppose you have a D flip-flop. If you have a D flip-flop, there is a D, there is a Q bar. You connect Q bar to D. Okay. Now what is going to happen? What is going to happen is it is going to function as T flip-flop. Okay. So we can use D flip-flop as T flip-flop. Okay. So this is how one can use it, and we can use any of the flip-flop as a toggle flip-flop, and I can design asynchronous counter. For that, what is required is simply what we do is, let's take 4 T flip-flops. I can draw like this vertically or horizontally, doesn't matter. This is T flip-flop. I am getting Q output, getting here Q output, that I am giving as input to the next flip-flop clock. I have T input here, that is 1. Okay. I have T input, that is 1. I am getting Q output, that output I am going to give it as a clock to the next one. Okay. Let us suppose that I am using active low clock. So negative edge triggered. Now I am getting Q over here, that I am giving as input to the next flip-flop clock. Now this is input T equal to 1. Now for all the flip-flops, okay, there is an output that we are taking it as, this is, let's say, flip-flop A, flip-flop B, flip-flop C, flip-flop D. So this will be QA, this will be QB, this will be QC, this will be, this Q is nothing but QT. Okay. Now wherever we are applying very first clock, here is the clock, right? That is LSB. This is LSB. Now whatever the output that we are getting is going to act as a clock for the next flip-flop. That is going to be next MSB. So the overall MSB is this. So you can observe QA, QB, QC, QD. If it is JK flip-flop, you will keep J equal to 1, K equal to 1. Same thing, output will connect it to the next flip-flop clock. So if you look at the functionality, if you look at it, it will be 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0. Likewise, it will go up to 1 1 1 1. How do we get this? This we have discussed in the class. Every time this will be going to 0 and 1, 0 and 1, 0 and 1, 0 and 1. This will be 0 and 1, 0 and 1, 0 and 1, 0 and 1, 0 and 1. This itself is clock for the next one. So it will get enlarged. Every time it is as if it is divided by 2. So this is clock for this. Once again I will get a, okay, 0 1 0 1. Next is for the next flip flop, 0 1 for the next flip flop. Likewise, okay, 0 1 0 1 0 1 continuously, 2 zeros 2 ones, 4 zeros 4 ones, 8 zeros 8 ones. If I add all possible combinations, I am going to get 4 zeros to 4 ones. Okay, this is asynchronous counter, which is normal counting sequence. If you want to stop the counting in between, what I need to do? I need to use clear signal. That suppose everything is having clear here, clear, clear, clear is available. Okay, so all clears are connected to 1. All clears are connected to 1. When all clears are connected to 1, when it is active low, it is going to function normal. Now when you want to stop it in between, based on the wherever you want to stop, that you can do it. What is that? Let's suppose I want to stop at n is equals to 5. Okay, modify counter. What is 5? 0 1 0 1. What I need to do? What is 0 1 0 1? This is 0 1 0 1. QA is 1, QC is 1. Okay, so what I do is I'll take all the clears together. I'll connect all the clears together. Here is a clear, here is the clear, here is the clear. All the clears I need to connect them. To this clears, what I do is I'll put an NAND gate, and inputs are one is QA, another one is QC. It's a NAND gate. When both are 1, output becomes 0, so it will clear that. That means it will come from 0, 1, 2, 3, 4, 5. Upon arrival of 5, it clears. Then it will start with 0. Okay. So similarly, mod 4 counter, mod 6 counter. For example, if you want mod 6, mod 4, 3 counter, what I need to do instead of QA QC, it should be QA QB, because QA1 QB1. Accordingly, you need to change the circuit. So this is all about ripple counter or asynchronous counter design. If you want a mod 10 counter, what I need to do? Mod 10 counter, 0 to 9. What is 9? How many flip flops required? 4 flip flops required. So what I need to do? Instead of QA QB, it should be QA QD. Okay, if it is a BCD counter, it will go from 0 to 9. What is 9? Is 100. Okay, mod 9 counter, 0 to 9 is 10. So mod 10 counter. Mod 10 counter, directly you need to connect it to what is 9? 9 is 1001, right? So QAQD, of course. That is BCD counter. BCD counter is also known as mod 10 counter. Mod 10 counter is BCDs is mod 10. Mod 10 is 0 to 9. Okay. So likewise, one can design any variety of asynchronous counter. Okay. Is that clear?